This is a demonstration showing how to use ShipSim to model a simple rib. There are two main parts to the simulator display. The instrument panel here can be customized by the user to include sliders, dials and readouts. You can add buttons to enable different input modes. For instance, if you are interfacing with the autopilot using analog input signals, you would enable the hardware button here. The mode buttons here give access to the different control modes within the simulator. The buttons here, start, pause and reset, control the simulator. The reset location and heading and speed can be set here. This blue screen shows the plan view looking down on the boat. Another option might be to use a chart view here or use a GeoTIFF background to the plan view display. In order to model a rib, we need to define the hull parameters and add the motor. For this simple model, I'm just going to control the engine RPM and the steering angle of the motor. So I've got two machinery channels to control. I add these through the machinery sockets dialog. So channel 0 is the rudder or engine angle and channel 1 is the engine RPM. I'm going to use the composite model to model the rib. So I set up the configuration via the composite model configuration dialog. I've set the hull to be 10 meters long, 3 meters wide, and calculated the displacement and moment of inertia. The centre of gravity is 4.5 meters in front of the aft perpendicular, so it's just behind the midpoint of the boat. In propulsion, we've got a number of different options. Here for the rib, I'm selecting a single swivelling thruster, and I'm controlling it via those sockets I defined earlier. So the RPM is controlled by machinery channel 1 and the angle of the motor is controlled by machinery channel 0. Most of the time, vehicles can be simulated using standard hydrodynamic and aerodynamic models. The hydrodynamic model here allows you to enter equations for the forces acting on the boat as a function of forward and lateral velocity and rate of turn. You can set up the equations for the x direction, i.e. forwards, y direction sideways, and yaw or n rotational directions. And you can also modify the added masses and the hydrodynamic centre of the boat. The aerodynamic model is more complicated and allows you to specify the force distribution as a function of angle of attack for each of the three components. The simulator includes a sea state model which generates a field of waves of realistic height and wavelength. The response of the boat to these waves can be defined here. The sensors are set up from a menu of options. Here I'm using GPS and a gyro compass. I've set the output interval to be 0.1 of a second on both, so 10 Hertz, and I want to enable RMC from the GPS and HDT and ROT on the gyro compass. We then configure a serial port to output that data on. And you can see here I'm outputting, I've got HDT, ROT and RMC all enabled and being output on that port, which is an RS-232 port, but I can equally use a TCP port or a UDP port here. Other options are NEMA 2K. So initially we can drive the boat around using the sliders and check we have a reasonable top speed and maximum turning rate. vehicle responds in the way we're expecting. Then we will want to connect to the autopilot. We have various options: serial, RS-232, 422, Ethernet, CAN bus, or analog digital PWM. Dynautics has developed its own analog and digital interface which can take these signals and use them to drive the simulator. The inputs can either be follow-up, i.e. an analog signal proportional to the demand, or rate control, in which case the magnitude of the analog signal controls the rate of change of the demand value. As well as the standard NEMA command messages for rudder command, we've defined a simple NEMA type message which can be used to send commands from the autopilot to the simulator. If I enable serial control, you can see that the simulator is now being controlled via the serial command interface and ignoring the sliders. In order to link the machinery sockets with the internal controllers, the heading hold, waypoint follow and position hold controllers here, we need to link the machinery with their effect on the boat. So for instance, RPM changes the forward motion of the boat and engine angle changes the rate of turn of the boat. We do this using the CAM, which stands for Control Allocation Matrix. So the rudder angle here is marked with that it affects the yaw, and the engine RPM affects the X movement, the forward motion. You can add a tide, wind and sea state into your simulation through the environment dialog. A schedule of changing tides can be defined. For instance, here the tide is 0 knots for the first hour, increasing to 2 knots from the south, then veering to 2 knots from the west. You can add random noise to both the tide and the wind vector to simulate turbulence. The wave model is based on a standard model of wave heights and lengths as a function of sea state. The water temperature, times and seabed depths are included in order to give realistic data for the NEMA output sentences, such as depth below transducer. Another way to visualise the boat's response, which might be useful for demonstrations or training, is to use the ShipSim viewer. This is a separate application which takes its position and attitude data from ShipSim and feeds it into a rendered 3D view. The user can add scenery and other ships into this simulated world and also change the visibility, the time of day and the sea state.